Cover measurement methods using ocular estimation in plots. There are a variety of measurement methods that can be used to estimate plant cover. In this lesson, we will be focusing on plot-based methods that use ocular estimation techniques. With ocular estimation, we most commonly estimate canopy and foliar cover. Occasionally, we may estimate basal cover, although this is less common because it can be difficult to detect the base of plants when there is a sufficient amount of above ground material covering them. In the diagram on the left, you can see a hypothetical plant community with a number of different species and several quadrats that are superimposed on this area. One of the advantages of using ocular estimation and plot-based methods is that with plots or quadrats, we have a greater likelihood of detecting rare and uncommon plants compared to methods that use points or lines. When we do ocular estimation, we are focusing on estimating the proportion of the plot that is covered by plants. So, for example, in the diagram on the right, we see 3 different plants of the same species that have their canopies outlined in red. Now, we don't need to estimate the actual area of each one of the canopies because we're more interested in the relative proportion of the plot that is covered by the plants. So we don't need an absolute estimate of area, but instead it's relative to the plot size. When we do ocular estimation, generally we use either square or rectangular quadrats, and we try to visually create proportional compartments of the plot. So kind of in your mind's eye, or by marking on the side of the quadrat, you determine what 5%, 10%, 25%, and 50% of the plot looks like. Then, by examining the plants inside the plots, we determine what the percentage of coverage is inside the plot quadrat. If we can determine what 5, 10, 25, and 50% looks like, then we can pretty much estimate to the nearest 5% most combinations. For example, we could estimate what 75% looks like by adding 25% to 50%, and we would see that it would occupy to approximately here. And by adding an extra 5 or 10%, we can change our ability to estimate. It's important to remember, if you're working with rectangular quadrats, that we may need to also have a visual estimate on what 25 and 50% looks like along the long axis of the quadrat. Before we begin doing ocular estimation, it's also always important to clearly define whether we're focusing on foliar cover, canopy cover, or basal cover. If you'll recall, foliar cover is the cover that is occupied, or the cover that is provided by the leaf material or the foliage of the plants, and it does not include the gaps in between the leaves. So you can see this halo in orange in this diagram here does not include the gaps between the leaves. Even though it occupies approximately the same area, if we focus on canopy cover in the bottom diagram here, we can see that by drawing a circle around the circumference or of the canopy of the plant, we would include all of the area that is inside this circle. Now with basal cover, we would only be focusing on that area that is defined by the base of the plant. It's difficult to estimate what plant canopies look like in square or rectangular quadrats, partly because canopies are rarely square or rectangular. They tend to be round or irregular in shape. And so sometimes, especially when we're trying to estimate foliar cover, we need to sort of deconstruct the plant. If we didn't do that, we might estimate that the cover of this plant here was approximately the same as the one in the lower diagram. But if we deconstruct it and sort of stack all the leaves together, we can see that rather than covering over half of the quadrat, it actually, the foliar cover here is less than half, more than 25%, but definitely less than half of the quadrat. Okay, so let's take a look at a slightly more realistic looking example. This is a plant community that includes a species of grass and a species of forb. We also see some ground cover that is represented in this diagram, and ocular estimates are sometimes used for ground cover, but for the same reason not as often as canopy cover, because the ground surface, soil surface, can be obscured by vegetation. If we superimpose a quadrat onto this community and then examine the plants one at a time, we're looking at canopy cover here, we can see that the canopy of the grass species is defined by this purple dashed line. Now I mentioned that it's difficult, even though we've compartmentalized the quadrat into, say, half, it's difficult because of the shape of the canopy to determine whether that's half. What I like to do is, in my mind's eye, kind of move that canopy over and then compare that to what I have as my marker in the quadrat. It's approximately half there, and so because this area does not occupy the corners, I would estimate that the area or the cover, the percent cover of the grass species is definitely less than 50%, probably more than 40%, and somewhere between 40 to 50%. So let's take a look at the forb species. Again, in my mind's eye, I draw a circle around the canopy of the forbs. We see here that it's patchy, and so there's some of the same species here as well as in here and here. And so again, in my mind's eye, what I want to do is take that area covered by or defined by the circumference of those canopies and kind of squish them over to the side of the plot, because I have determined these compartments for this particular quadrat. By doing that, I can see that the canopies of the forb species is less than 25%, which would occupy out to approximately here. It's probably more than 15% and something less than about 20%. So I would estimate the canopy of the forb to be somewhere between 15 to say 18% cover. Now, from this exercise, you should be able to see that it's very difficult to estimate canopy cover to the nearest percent. It takes quite a bit of training and practice and retraining and calibration. It is something that can be done, but there's always some level of uncertainty about the precision of your estimates. So that's doing ocular estimates to the nearest percent. We do have other approaches in which we estimate cover ocularly in plots, but by using cover classes. There are a variety of cover class methods, and we're going to focus on the Dobbin Meyer cover class method. The Dobbin Meyer method is a semi-quantitative approach that can be done quite rapidly, and it eliminates the need for precise estimates, meaning that we're not trying to estimate to the nearest percent. Instead, we estimate the amount of cover into 6 different cover classes. So if we can determine what 5%, 25%, 50%, 75, 95, and 100% cover in the quadrat looks like, we can apply the Dobbin Meyer cover class method. Dobbin Meyer works by determining or assigning cover to one of 6 classes. These are cover between a trace to 5%, or for class 2, anything greater than class 1 but less than 25%. Class 3 is anything greater than class 2 but less than 50%, so between 26 to 50%. Class 4 is anything greater than class 3, so greater than 50% but less than 75%. Class 5 includes the range between 76 to 95%, and class 6 includes the range between 96 to 100% cover of the plot. Now, the Dobbin Meyer method was originally developed using a 20 centimeter by 50 centimeter rectangular plot with specific markings to facilitate determining what the classes were. We see a Dobbin Meyer plot here superimposed over a hypothetical plant community. And just to remind you, there's class 1, trace to 5%. Class 2 is 6 to 25%. Class 3 is 26 to 50%. Class 4 is 51 to 75%. Class 5 is 76 to 95%. And class 6 is anything greater than 96% cover. So let's see how this works with these plants to try to estimate canopy cover using the cover class method for each of the species in this plot. Recall that when we're estimating cover using plots, we don't estimate the cover of the plant material that is outside of the plot. And so, say for this grass plant here, we would be focusing on the cover that is included along the boundary here until you get to the circumference of the canopy and then back to the boundary of the plot. The grass plant not only occupies this corner of the plot here, but there's another plant of the same species over here, and so we would include all of the plant canopy here, exclusive of what's outside of the plot, and add that to the plant canopy over here that is inside the plot. By doing that, if we try to move in our mind's eye the canopy cover from here over to here, we can see that it would occupy over 25% but less than 50%. And so it would be assigned cover class 3. For the next species, this one here, we can see that this individual is definitely smaller than the 5% that is delineated over here. We do have to include this portion of canopy of this plant because they're a member of the same species. But even if you added this part of the canopy to this one, it would still be less than 5% more than a trace, so it gets assigned cover class 1. The same thing for this small annual plant represented here. There are a number of them, but if you added them all together, they would still be less than 5% cover. The forb species outlined here is slightly more than 5%, and so it would be assigned cover class 2. Now this plant here does have a trace of canopy that occurs in the plot, and it would be assigned cover class 1. So how do we use this information then to determine canopy cover? What we do within each plot for a particular species is we assign the midpoint of the cover class range as the amount of canopy for that particular quadrat. So for example, for all of the species that were assigned to cover class 1, we would assume that we would assign 2.5% cover for those species. For the forb species that was cover class 2, we would assign 15%, and for the grass species cover class 3, we would assign 37.5% cover. Now you may say, well, that's too much. 37.5% cover is far more than the amount of cover that we see for the grass species here. It's barely over 25%. Well, that may be true, but in a second quadrat, for example, if we had more of the grass species, that would bring it up to close to 50%, but not over 50%, it would still be assigned class 3. And so if we take multiple observations in multiple quadrats, it balances out in the end. That's the way that the Dobbin Meyer method works. You have to have a large sample size in order for the estimates to balance out. And that's why it's called a semi-quantitative method. So let's look at an example calculation. This is with a small number of quadrats. 5 quadrats were observed, and we're going to look at the cover class for just one species. In these 5 quadrats, they were assigned cover class 2, 3, 3, and 1. In quadrat 4, the species did not occur, but we do write down a 0 because it's not that we didn't observe it, it's that that species did not occur in that plot. So we would then assign the midpoint value for the cover amount for each one of these quadrats. So 15% for class 2, 37.5% for class 3. 0 gets scored as a 0 because there was nothing, this plant did not occur in that plot. And for cover class 1, 2.5%. If we add these and then take an average of the total number of quadrats observed, which was 5, that would give us 18.5% cover for this particular species. And remember, the way that it works for the Dobbin Meyer method is that we require a large sample size. We save time by not having to try to estimate coverage to the nearest percent and only assigning cover class. And so we can measure more quadrats. Usually the Dobbin Meyer method is done by placing quadrats along transects, and we would need multiple transects with multiple quadrats. So in conclusion, using plots, ocular methods are commonly used to rapidly estimate cover. They're very good for monitoring because it can be done rapidly, and because we can use this approach to detect uncommon species that we would not find using point-based methods, or we would be less likely to find using point-based methods. One of the disadvantages of using ocular estimation in plots is that it is subject to bias, or the potential for bias. And so observer skill is very important. We can improve observer skill by spending time on training and calibration in the field. Cover class methods are commonly used because they are an efficient alternative to estimating cover to the nearest percent.